So hi, I call this talk Advanced Microservice Concerns. My name is Steve. I work at a company called Third Channel in Boston, Massachusetts, in the U.S. Let's talk about microservices. So before I begin, I should probably point out that there's not much in this talk that exactly is Groovy related. In fact, there's not really any code in this. It's mostly just theory. But I believe this information is useful, and I think Yvonne and Roberta did too when I asked me to speak about this stuff. At Third Channel, we love microservices. Groovy is our most used language in services, and maybe there's some implementation there. I'm not sure. Anyway, the agenda for this presentation is to first briefly cover the microservice architectural pattern, some of its advantages, and possibly the disadvantages, and then get into some of the advanced concerns, where I group them by their overall topic, service design, organizational structure, and DevOps. First off, probably begin with, has everyone here heard of microservices? Is anyone here actually using them at work right now? Yeah. I'll just go with a quick overview of what I believe the microservice pattern represents, and I think their whole purpose is to fight against a distressing pattern in software architecture called the monolith. So monolith has become, I think, the natural response for many developers or companies when they first start out a project. And when we say monolith, what we're talking about is a single, where your application is a single, logical, executable unit, often comprised of, at least in web applications, 3 components. Your view layer, your CSS, and your JavaScript and your HTML. The middle tier, where it contains most of your business logic, and then the data storage. Here's a quick representation of an example e-commerce app's sort of middle tier. The square box sort of represents that logical unit, whether that's a WAR file or a jar file that you're deploying. So we have broken up into little components. So we have product catalog, the general site administration, the order history service, and the billing component. As I add features to my application, I simply tack them inside that logical arm, and it keeps getting larger and larger every time I deploy it. And again, this the danger, I think, with the monolith pattern is that this feels like the right thing to do. Right? When I start a new project, I choose my framework, and I begin building it. You start out easy. Your quick wins as I add new features. It's like, oh, now I need a shopping cart. Great. I'll add the shopping cart model and the controller, tack it in, deploy, and test. In the long term, though, you will run into problems. Complexity grows quickly as you keep adding new features. Even if you're very, very careful, the application will inevitably become a mess. You might say, but I have distinct surface layers in my application, keep things nice and separated. I follow dry principles. I'll never have that problem, but you will. You'll throw in quick hacks here and there. You'll amass technical debt that you never go back and fix, even though you swore to yourself that you would. It gets to the point where you open up your IDE and you just have a mess of controllers and models and all sorts of things, and no one in the company or anyone in your team really understands the whole thing. And adding new features or bugs, developers will spend huge amounts of time figuring out how something works before they can even start the project, right? So if there's a bug in the billing service, I have to look at the whole thing, see how it interconnects with everything else, try and figure out the exact spot where that bug might be occurring, make the change, and then hope I didn't break anything else. Oftentimes, this might require dragging in other developers to help you figure out what's going on in the system. Twitter has a blog post where they call this approach an archaeological expedition, where they have to go through and sift through the entire history and kind of bring people along with them in order to figure out what to do next. So this frustration of working on large, monstrous applications, I think, is why microservices have become so popular. So when we use the term microservice, what exactly do we mean? Well, fundamentally, what we're talking about is building a distributed application. So instead of the monolith I showed you before, we said do this. We break up each of these components into their own separate executable units. just service-oriented architecture. People have been doing this for a long time now. And in a way it is, but SOA has been around for years now, but microservices, though, are a much more focused and disciplined version of this. The reason being is that it involves technical and organizational changes that are not defined within service-oriented architecture. Let's go over a few of them. First off, independence. In a microservice system, each service should be completely independent of each other. Now, this means that they're individually deployed. They have their own separate code repository, and they're independently developed. Having them in their own code base, for example, allows you to have independent history of how this particular feature evolved too, which is kind of a nice thing. This results in nice, isolated, separated code, which is great for adhering to design principles like separation of concerns, and we all hear that term, we know it's a good thing. So this is taking it to the extreme level. Each service contains a single context, or rather each service is responsible for one thing. And this is what we say when we mean micro. So it's not so much that there's some arbitrary size that these things have to be, like 500 lines of code or something. The size of a microservice should be enough to fit, where one developer can fit the entire thing in their head and understand everything that's going on while maintaining the entire scope of the application within their brain. Now this approach then leads to smaller, less complicated code bases. So again, let's say I was building an e-commerce application. I have my product catalog, I have my administrative service, I have my billing service, I have my order history service. Each one of them will be developed separately from each other, and it will be far less complicated than if we try to jam the whole thing together. Now they do need to have a way to communicate with each other, and when you do so, it should involve simple, dumb communication technology. But each service should be very smart about how they do so. Which basically means no enterprise service buses. Has anyone heard about the enterprise service bus? Oh, yeah. So you would often find these in service-oriented architecture deployments. Generally, they are very complicated pieces of code that involve lots of logic about how messages and communication should be routed. Now, in practice, these often become very complex and need to maintain a bunch of custom logic for manipulating messages, and it just becomes another massive thing that you have to maintain. So instead, microservices call for using, generally, either HTTP or message queues. HTTP, because we're already building a web application, why not use built-in native web technology? HTTP allows for direct communication between services, but it has the disadvantage of being synchronous. So while the request is active, both services that you're communicating with have their resources locked during the course of that communication. Message queues, on the other hand, are asynchronous generally, but require some additional code or another library for messaging formats. So you have to spend time developing sort of the library that each of your services will use to facilitate communication, whereas with HTTP you get communication out of the box. So if you're using HTTP-based communications, you have a handful of services, you may end up with something like this, where I might have multiple product catalog services that know how to communicate with the administration service, which know how to communicate with my order history services, which know how to communicate with my billing service. And it can quickly become a mess of interconnected services. And each service needs to know the address of the other services and how to reach them. So if a user places an order, that code needs to know how to talk to the order history service and the billing service in a particular order. And then has to talk to the inventory service to make sure that I have proper inventory and things like that. To help manage this, though, you end up having to use another service to help you identify the locations of these other services. A service discovery service. Netflix, for example, has released their internally developed version of this called Eureka, which is on their open source library, which is very useful, and people seem to love it. And basically what happens is when a service comes up, it registers itself on the Eureka service. So when one of your other services says, okay, I need a location of a billing service, you don't maintain the address of the billing service in your particular location. It asks Eureka for the first available. With a message-oriented approach, on the other hand, services don't know where each other are. They don't need to know about the address. They don't need to worry about. Don't even need to worry about who they're talking to. Not necessarily. They just need to know that if they send data or ask for data, that they're going to get a response by broadcasting a particular event. When an event needs to go out, it is simply generated. I don't need to post it in any direct service. I don't need to. If a user changes their address, I don't need to inform other services that the user did that. I just broadcast user address change. And anything that gets to listen to, so it can. I prefer this approach for a variety of reasons we can't already tell, which I'd be happy to talk to anyone about this later. The interesting thing about this, though, is that you do need to introduce a new service that routes the messages, a message broker or message queue. And the services do need to know the location of that particular broker. And this broker can be a cluster, for example, it doesn't necessarily be a single service. Regardless, there's two options I think that are very useful for this approach. RabbitMQ is sort of the classic, I think. There's another great example of Kafka, which is an Apache project, which I'm thinking of switching to. We use Rabbit right now locally, but I hear really good things about Kafka. But they're a little bit different in how they operate. Kafka is more native and uses a bunch of little Linux. I think this is correct. It's a bunch of little Linux operations. RabbitMQ is built on Erlang. It's a little bit higher service. But it was developed for trading software, so you know that. So, people that work with money need stuff done. Yeah. Lastly, so microservices also should concentrate, while they should concentrate using very simplistic channels, they should also be very smart about how they do it. They should also maintain RESTful communications. I feel that when many people think of REST, or say that they have a RESTful API, what they're really thinking is they perform CRUD operations, create, read, update, delete, over HTTP using the HTTP verbs. And that's not really what REST is. There are many more aspects to it beyond that. For example, no state should be shared. When these services are talking to each other, they need to be as stateless as possible. For one, trying to maintain shared state across a distributed application is madness. The REST specification also calls for caching your data, which is great, of course, caching data, layering your services, and ensuring that they have a uniform interface. When we talk about layering, what that means is that if I'm sending data, as long as the data is handled, the service should trust that the handlers know what to do. If that data needs to be passed on to another service, they don't need to worry about that. A uniform interface implies many things, but we're going to take a shortcut and just say that each of your services should communicate with each other via the same standard technique. If anyone wants to argue about habeas, or hypermedia as the engine of application state, I'll stand up to do that. Lastly, from an organizational standpoint, the teams building the service should be cross-purposed and dedicated to that particular service. Teams in charge of the service should come from a variety of disciplines: engineering, QA, art and design, project management, perhaps a deployment engineer, etc. I'll get into more of this later. This is a very important subject. Microservice architectures have been gaining huge followings in the past couple of years due to some of the benefits they bring. Because our systems are independent of each other, like I mentioned earlier, this promotes natural loose coupling. Individual teams can develop their services independently of each other. Complexity. Each service can be built according to the technology that best suits it. You're not locked into one language or one framework. So if Node.js is better for one particular service, build it in Node. If Grails or Spring Boot is better from another application, build it in that. If Postgres is the ideal database for this particular service, awesome. If Redis is best for this other service, fantastic. We're not locked into any one thing. But of course, we're always going to use Groovy, right? It's easy to scale microservice applications to meet particular user demand. This is, I think, is a very, very important topic. By making these smaller services, what you end up doing is being very, very efficient about how you scale things. So as demand for the application grows, I can scale just the components or services that I need, rather than needing to, in a monolith application, redeploy the whole thing behind some sort of load balancer or something like that. If my application is in one WAR file and I need to scale it, what I end up doing is making a whole new instance of this massive piece. And if I just have a lot of traffic on my order history service, I can scale just that a little bit. I borrowed this slide from Martin Feller's website. It's a very good discussion about this topic. So what this does is it allows for targeted growth. So you know that if a particular service is getting a lot of attention, you should focus more of your internal development resources on it. And from a computational standpoint, it also makes you more efficient in how you're spending your money in terms of your computational resources. So if you're on AWS, being able to target exactly how you grow, where you grow, it keeps your build time. And speaking of scaling, I think this is probably my favorite aspect about this. Is using microservices is easy to scale development. So scaling development is generally very difficult. With a microservices architecture, you have an advantage where it's relatively easy for developers to work with this approach. Because the complexity for a given service is smaller, it's easier to reason about. It's easier to find bugs. It's easier to know that if I need to build a new feature, I know exactly where it needs to go because the service is relatively small. I can fit the entire thing within my brain, know exactly where I need to be, and fix the issue, or add the feature. Microservices also allow us to fail fast and to start over. If we find that a particular technology or a particular approach that we're working on isn't working, it's easy to refactor or replace the service. Has anyone here ever worked on a team with them on the collective level? It's not so good. It's difficult. It can be difficult to wrap your mind around distributed systems and how things are all interconnected. Splitting your code into services can add additional operational complexity, because you might have some more moving parts, and it can add some communication lag. So if a service has to talk to 3 other services and it's doing it over HTTP, that can add some additional time to that request. I disagree with this one a little bit because by splitting things up, you do inherently reduce the complexity of the individual service. You may hear someone in your organization say, "Well, what if service X goes down? It's central to our business." That person is not ready for microservices. That's the wrong thing to say. Microservices also require some additional focus on DevOps-related work, like streamlining deployments and getting these things up on wherever you're handling Cloud Foundry, AWS, things like that. These can all these problems, while valid, can be addressed, reduced, or handled. These next sections cover some of these advanced concerns when working with microservices. They are things that everyone should be aware of. So first, service design. As we're building our individual services, what should we be aware of? I'll reiterate here that each service needs to be a single bounded context. It's a bit tricky, but this point basically states how large a service should be. Again, it's not any particular line size or anything like that, but service should be small enough that it fits within the entire functionality, fits within a single developer's mind. Your services should be resilient, which means that they should embrace and welcome that errors will occur. The service will probably go down at some point, and they should know how to handle any potential error. So if our order billing system goes down, the site shouldn't shut down. We shouldn't break, but the product browsing system should say, "Oh, I'm sorry, your orders are temporarily down, but hey, keep adding things to your shopping cart." Or better yet, take the order, put it on a queue, and then process the order once the service comes back up. I should still be able to administer the site. I should still be able to get users. The overall rule, I think, is that your services should maintain their independence, just like we talked about earlier, and fail independently as well, not bring each other down if something crashes. Because we have that additional communication lag between each service, we have to make sure that each of our services are as fast and efficient as they possibly can be. You should strive to return a result as a service. When you maintain a service, you should strive to return a result as fast as you can. In the U.S., we have an idiom called hot potato, which means to get rid of something as fast as you can. Speed is king. Several years ago, an engineer with Amazon named Greg Linden revealed that the company ran an experiment where they intentionally slowed down their site performance, and they were able to demonstrate that a 100 millisecond delay, a tenth of a second, resulted in a 1% drop in sales. Now for Amazon, that's millions of dollars. Right? So just that small percentage in speed means that they were able to take less money from people, which It's interesting. I used to work as a consultant, and I would go and I worked with e-commerce companies before, and I would go in and I'd say, oh, you're doing X, Y, and Z wrong. You're not handling orders in a queue. Your site's performance is really slow. Like there's a physical limit to how much money you can take per day. If you would just implement these features, you would make more money, and they didn't listen. And they were just completely ignoring everything. Each service should be responsible for one particular thing within your application. This relates to the single-bounded context, but it sort of spelled it out. Each service should be an authority on some data, or an authority on a particular process. For example, I may have a user service that is the source of truth for users within my system. Or I could have an email service that's responsible for broadcasting emails, managing templates, and things like that. Next, embrace eventual consistency. Has everyone heard of eventual consistency before, or aware of the concept? And so basically what it means is that I couldn't really think of a good diagram for this, but in a distributed system, you must accept that an individual client or service may not have the most recent view of the data. Eventually, every service will have their view of the world consistent with every other service, which is an interesting concept. And sometimes people who come from an ACID environment that want high consistent, I'll get into more of this later too, but want highly consistent data are generally scared of this sort of thing. All my data is not up to date all the time, and then the question that you should ask these people if they ever bring that up is say, okay, well, if someone accesses your data, do you lock the row in the database to prevent anyone from adding more data? Right. So if I bring up a user on my web page, is that row locked from being updated? No, generally not. Right. So somebody could come in and update that user. So the second you bring it up onto the screen, it may not be consistent with the data that's in the database. It's an interesting sort of nuance. So these next two topics are perhaps, I think, the most difficult in this talk. It's hard to understand, and it's going to be hard to explain too, so I'll do my best. First up, something called the CAP theorem. Anyone heard of the CAP theorem before? Yes, very good. So basically the CAP theorem states that there are 3 attributes or 3 guarantees that we can make within a distributed system, or 3 things that a distributed system can offer us. One, consistency. When an update occurs within the system, all services know about that update when it happens. And so like I just said, it's probably not so good to be known. Availability. When information is asked of a particular service, it responds as quickly as it can. And partition tolerance. A service is able to handle or deal with failures occurring in other services. And for a distributed system, you're only allowed to have 2 of these attributes at any given point in time. And I think, based on what I talked before, you can probably see where I might be going with this. This was originally called, a little bit of history, this was originally called Brewer's conjecture. And it was actually proved in 2012, and so it became a theorem. Incidentally, this paper is also where the term eventual consistency comes from. Eventual consistency comes from. It's interesting because I thought it's been around for a long time. It's only 3 years old. CAP decisions can be service-specific as well too. This is one of the key takeaways from the paper, is that it's not all or nothing. 2 points out of 3. Each service can have a varying degree of these things. So I could have a system that's highly consistent and is a little bit available and a little bit partition tolerant. In general, though, especially with working with web apps, it's very important to have highly available data and high partition tolerance. Like the user will forgive you if an email maybe doesn't go out, or if maybe they have to make an update twice or something like that. But if but banks are money, though. When you think about money, you want to be highly consistent. People get really upset if their balance is not, they found it in the bank. Last, let's talk about data locality. You should be very, very concerned about data locality, which is a weird term, and I'm not actually sure what it means in English either. There are 2 aspects to this concept. One, spatial. So how how far away is my data when it's stored? So in a single database, data can be considered highly spatial if it's in the same table. Data which is reachable by joins is less spatial because it's a join away. In a distributed environment, it's a service call away. So data which has these steps to reach is less efficient to access. Temporal, being highly temporal means that the data is read frequently. So highly temporal data is an excellent can be an excellent candidate for caching, for example, especially if it's not updated very often. Again, these terms take on a very different meaning in a distributed system. So in an ideal distributed environment, each system would be completely separate. Each system is an authority on a particular set of data. However, there will always be some conceptual overlap between our data or our objects. So for example, let's say we have, again, the e-commerce system, where we have our web front end, and then we have our user service, and then we have an order history service, both communicating over RabbitMQ in the middle there. The order history service maintains order information about the users, so anytime a user makes an order on our site, we keep their history so they can look at it later. The order history service needs to have some understanding of what the user is. It doesn't necessarily need to know their name or their email address, but it needs some sort of, its concept of what the user is really just the user's identifier, which is generally fine in this case, because there's that data will not really have to be updated. The user's ID is probably not ever going to change. But so the same chart from before, but let's add another table. Communication. So let's add the email communication service down there. This service also conceptualizes the user, but with a different subset of information. So I still have the identifier, but I may also have the user's email address on there. So if I store the email address on the user service, which should be the authority about the user's email address? So my email server uses it more often. Every email goes out, I might be using that email address. But that email address is key information about the user. So which service is the right authority on a particular email address? It's a tough choice, I think. But you don't want the data to become too to spread out too far. It's a tough problem, I think. So one compromise is to, unfortunately, synchronize the data. To synchronize that email address across both services. So if a user updates their email address, I could broadcast a message that says, hey, email service, the user updated their email, here's their email address, save it in your system. Or we could remove the email address entirely from the communication service. So the user has no concept, or the email address has no concept of the user's email address. But simply blindly sends emails out. So if the email service gets a notification, instead of saying, hey, send the email to this user, it says, hey, send out this email, here's the email address you want to send to. That way there's no data synchronization, the user service maintains the authority. Or third option, we can cache the email address on the communication service, so then if the email service gets a request to send out an email, and it says, hey, send it to this user, the email service could say, well, I don't know this user, what's their email address? And then ask for it from the user service. Those are all some different strategies. I don't know if either one's actually the best one. I very much dislike syncing data. So my recommendation is to not use the data synchronization option. And emphasize that again, do not sync data as much as you can. There will inevitably be some points where you will have to synchronize some data, but try to keep that down as much as possible. Because inevitably, what's going to happen is the data will become out of sync. So even if my best intentions keep that user email address in line with what's in the user service, eventually some users' email addresses will drift, and they may not get updated due to network problems, or maybe they get the message, or maybe there's an error. You might think you've unit tested these services, so you're sure that it'll never get out of sync. It will. And then you'll have to go and create some jobs or processes to go in and resync data between systems. Like every now and then I'd run a job that says, okay, update, make email service will have to go and update every user's email address and make sure that it's up to date. So we've tried synchronizing some data to the channel in the past, and these data discrepancies were the primary cause of bug reports. It's terrible. So basically, if you overhear anyone on your team say, we could just synchronize it, immediately roll up a newspaper and whack them on the nose like a dog. Horrible. So the goal with microservices is to have highly spatial data and efficiently handle temporal data. It's a very tricky concept, but it's basically the primary thing I think you should be concerned about if you're trying to work with microservices at this point. Next, organizational structure. So, like I said earlier, you're going to want cross-discipline teams. So each service should have a team assigned to it that's made from a variety of disciplines. So some companies will tend to break down their tech workers into different groups. So you might have the QA department, you might have the user experience department, have all the engineers sitting together in a cube farm somewhere, and you might have the DBAs tucked back in a corner. But microservices say, don't do that. Instead, break them up and make teams of various disciplines suitable for that particular purpose. Put a UX person along with a QA person along with an engineer, have them sit together, have them work together, and don't have these labels as the UX team or anything like that. One of the best experiences I ever had working with a given team was something like this. It wasn't on a microservice, but we would have these small little teams focused together working on a particular feature within the site. And I literally had the QA person sitting right next to me. So anytime I would commit code, she would see that it happened, pull it down, run her test that she wrote, and immediately say, you broke it, fix it now, and I would fix it before she could even complete a JIRA ticket. And it was this great little iterative iteration that I think could only happen by having us so close together and working together. With that, each team is ultimately responsible for the individual services. And when I say responsible, I mean it. So if the service malfunctions over the weekend, guess who's fixing it? That particular team. This is if you commit code, you're responsible for fixing it. And what this tends to do is to make sure that your team members will naturally start writing a lot more unit tests and make things as solid as possible before it goes out, because they do not want to get texted at 3 in the morning and have to wake up and go fix something. With that, your team should also be highly autonomous. What that means but they also need to be highly aligned with the business. So essentially what this means is provide your team or teams, I should say, should be provided with an end goal, but given the freedom to choose the right technology and the right strategy to get there. Because you shouldn't necessarily care what's going on in the service so long as it responds to the particular API calls as fast and quickly as it can. So I borrowed this drawing from a Spotify blog post on their engineering culture. And we'll get into a little bit more later, but they're a great example for how to structure teams. So basically what this is saying is that the boss is saying we need to try and cross the river, and get a bunch of happy developers, and he's letting them choose the best way to do it. You will need some architects or some team leads to champion this microservice vision. These people will need to have, again, the vision or the direction to guide and lead people. This leadership team may not necessarily have to be one person, but it could be a small group. They'll need to maintain the shared vision from which they can guide the rest of the company down this microservices path. Because if you try this right now, you go into New York and you have the power to make this change, let's say, you were going to find people in your company that disagree with it. They'll complain for all the various reasons I mentioned earlier. Building a distributed system is hard. I got to build a whole new service for each new feature. But what they're really saying is that this new approach is too hard, and they're afraid. The leadership team must be there to guide people and to educate them, and to reassure them that things will be okay, and to encourage communication, which leads to the next point: Conway's law. Who here has heard of Conway's law? All right. So I talked a little bit about this when I was at Greach last year, and I was actually at another conference a month ago, and it was all about microservices, and every other talk was about Conway's law. It's interesting. Basically, I'm just saying that I spoke about it last year, so I'm going to put trends in there. Basically, what Conway's law says is it's somewhat tongue-in-cheek, but it was written in 1968 by this guy named Melvin Conway. And basically what he's saying is that the structure of any given computer system will begin to reflect the social structure of the people who built it. So what that means is if you have someone who doesn't talk to somebody else, their particular bits of code aren't going to work together either. So while teams should be organized around services, these services still need to communicate. If Conway's law is not observed, you ignore this, some interesting things can happen. You may start ending up with situations where your intra-service APIs are not matching up. You may make a call and the field can be completely gone. Teams expecting data to be in services may not actually be there. A misunderstanding of what a service provides Team A, a misunderstanding of what service provides, may enter situations where one team might be waiting for another team to finish their service, and instead of trying to help them, they'll just sit there and say, Team B's not keeping. I can't do anything until they're finished. And eventually you may get to a point where teams start blaming or attacking each other for problems within the system. So, there can be arguments and attacks where, you might say, man, the team working on the shopping cart service is terrible. The code is always broken. Instead of trying to help them, you just sit there and, shut down. It's avoiding Conway's law is not easy, and I don't think there's really a clear way to do it. But it's, you have to try your best to encourage communication between, and collaboration, importantly, between teams. Some suggestions I've seen have been to rotate people throughout teams so they can see what it's like working on these other services. Get everyone on a shared communication channel. Slack is a very popular choice. Does anyone here use Slack? Yeah. Do you know it's valued at $2.8 billion right now? Nuts. But one important thing to do, especially with the microservice approach, is to ensure that each service's API is published and highly visible to other teams. Jeff Bezos at Amazon famously, a number of years ago, released a memo that basically said all teams must now communicate via the API. So they had to have a published, documented contract that they had to adhere to. And they were one of the first, what came out of that was essentially AWS now, because they started building all these little services. They realized that they could sell this approach to other people. It's interesting. Spotify is also very good at this. They have what they call tribes and guilds, which are strange terms to describe developers. But they have small teams of people focused on a service, which can be grouped into sort of the operational area of that particular those group of services. Like I might have a set of services that are related to, let's say, the users in my particular e-commerce app. Maybe there's something involving user, maybe there's something involving order history, maybe there's something involving sharing or notifications. So I might have a section of my tribe is sort of based around the user services, and then they have guilds, which are sort of the UX and the DBA teams, so they can talk about what's going on in their individual services, so they can share information about what's going on in their teams. Next, DevOps. I'll go quickly through this one because I only have a few minutes left. But because each team is responsible for their deployments, like I mentioned earlier, nearly everyone in your team is going to get some DevOps experience. Because you're involved with maintaining and also involved with deploying it, everyone's going to have to get used to this, whether they like it or not. First up, it's very, very important to have centralized service monitoring and logging. It's absolutely vital, an absolute requirement. This monitoring, and generally this is generally done by having another service in your platform that's responsible for performing heartbeat checks on your services and gathering metrics about them. It should be responsible for also acting as a centralized logging platform for each of these services. Right? Because if you have a bunch of services, you don't want to have to go in, SSH in, look at the logs for every single one. It's really good to aggregate them all in one location that you can go back and look at it later. You may be thinking, well, that's going to be a ton of data if I have a bunch of services. You're right. There's many applications or paid services out there that store and visualize this data. Many people I spoke to recommend this open source Elk stack, where you basically use Logstash to process your logs, put it in Elasticsearch for easy querying, and then use a visualization tool called Kibana for nice metrics and graphs. If you can get data from services and be aware of what they're doing without having to SSH in, you never have to SSH in, then you're doing it right. I read somewhere that some companies will actually block the SSH port, me too, on their instances of their Amazon VPC just to prove the point. Even if your services use different languages or frameworks, do your best to make sure that everyone is using the same general approach to the containerization is the new hotness, and things like Docker or Rocket can make a very standard way to deploy code. It's also very important to have small, fast deployments. So an approach where, like let's say a no-button approach. If I push to GitHub, it gets built with something like CodeShip because an image is created in Docker Hub and then it automatically goes out. That can be very efficient. A little bit scary, but efficient. Lastly, continuous deployment. Your engineers should be releasing things as soon as they are ready. Push a feature when it's complete, get it out the door. Now, I wasn't trying to diagram this either, but one thing that should concern your team are the moments where a release does have dependencies on other. So I have to deploy service C before I deploy service A, or else B will break. However, these cases should be rare. And generally, this will not happen, but someone will bring this up, guaranteed. The day-to-day deployments, though, will be amazing. Push code is done, it's out in the wild. I may not have tested it, so I may run into a bug, fix the bug, goes back out, fixed again. Once you get there and you're able to do that, it feels great. So, that's really all I have, I think. But in summary, let me give a quick laws of the microservice. Be independent, but at the same time communicate with your coworkers. A well-designed system requires constant communication between your team members. Keep your data close and cache it well. Do not sync anything. And get some excellent monitoring in place, and always move towards continuous deployment. With that, I thank you. I have 8 seconds left. Is there any questions? Yes.
Are there some criteria how we should divide our application in microservices?
Great. That is a great point. So the question was, is there any criteria around how I divide services? So if you've been building your application already with nice service layers or nice individual services, then you have a good place to start from there. You may look at your code and realize you already have a file called user service. And it's a little bit tricky because a code level service and a microservice, separate application deployable thing, is also called a service. So it can get a little confusing when you're thinking that. But in general, I think it's good to break. To take a component of your code and mentally break it down to the point where you can reason about it all at once, and it's as simple as it can be, and start extracting bits like that. And if you're moving to a microservice approach from the monolith, a good way to start. That's actually what we're doing in Third Channel. Is we started out with a monolith, and now we're breaking it up. All new features that can be reasonably thought of as a service. Start there. Set up the communication channel, and then slowly extract bits and components from the original monolith, and make new services out of them as we have time. And if you need to, if someone says we'll go add this feature, or go update this particular bit of the code, go refactor it. That's a good point to extract. Does that make sense?
Yeah.
Any other questions? Yes.
If you use a message broker
Yes.
to communicate with your services, there's two things I cannot figure out how do you implement circuit breakers and also RPC style communication.
Right. So that's so the question was, if I'm using a message broker, how do I do things like circuit breaking or RPC calls? And so I'm not 100% sure what circuit breaking is. As far as I understand it from at least what I've seen on presentations from Netflix, is if I start seeing a bunch of errors prop up in my service, and correct me if I'm wrong, if I start seeing a bunch of errors prop up and I see if I'm monitoring it and I see a high rate of failure, I shut off a service, so it will so it will stop breaking until I can get to the point where I can restart it, and then I start letting traffic back in until I'm satisfied that it's up and working again. Is that right?
Yeah, it's also related to responsibility. It's not that the wrong engineers get woken up at 4 o'clock in the morning. It's just that the guys who actually broke the service get woken up.
Gotcha. Yeah. I haven't had to deal with that yet. But
Good.
right, which is great. And then, sorry, what's your second question?
RPC.
Good, okay. Because there's somewhat, I think, so RPC is relatively easy with the message queue because a lot of times, at least with Rabbit, you can programmatically generate temporary queues. So one strategy, when this would be better with I have a chalkboard. this would be. What's that? Yeah. All right. I have horrible board handwriting, so nobody judge me. So I have service A, and he's to ask service B for information. They have the message broker, and then B and A have the regular, let's say, queues. And these queues are monitorable, so I can see, to go back to your circuit breaker question, I can see how large a particular queue is if it's filling up. And if I have multiple instances of A that are all listening on this queue, for one, that gives me neat scaling, because if I see this queue getting extra large, I just add more A instances, and if it's completely drained, I can shrink the number of A's I have. So for a circuit breaker problem, I'm sort of jumping around here, I apologize. If this thing gets filled up and my internal service is detecting a whole bunch of errors coming from A, I could probably wire up something to sort of shut this down for a while, and then programmatically revive it. That's an interesting subject. I'd have to explore it. I think it's fascinating, and I'll have to worry about that at some point, I'm sure. But for the RPC style, if A needs to ask a question of B, B receives A basically sends a message out in the queue, goes up in B's box or B's queue. A asynchronously hands that off. Or well, no, sorry, hold on. It could. There's two ways. One, it could asynchronously hand it off, and then have some sort of command object that's sort of waiting for the response to be regenerated. B's response will need to have a unique identifier of which A service it was, and then it can resume operations once it sees the message come back in. That's nice because it's asynchronous, but it's additional. It can get complex because you have to worry about which service it's going back to, and what's happening over what A was doing when it asked for the RPC call. It may not be able to asynchronously to wait for a response. So what we do is if A needs to ask for data from B, it sends B a message saying, hey, I need, or it basically emits a message saying, hey, somebody sent me this user information. It doesn't necessarily know it's directly talking to B. It knows it's talking to a service that responds to give me user information. But it also generates a temporary queue that's unique to A. And this is a randomly generated UUID. And it passes along in the message saying, hey, when you have this answered, send it back to this queue. And so then A gets the message and deletes the queue.
That's great.
Does that make sense? It's a little wild when you first hear it, and it can be a little scary, but it seems to work really well in practice. Any other questions?
How about duplication, data duplication?
So how about code duplication? So you're saying, if I have a nice utility class in A, do I use it in B?
For example, I'm thinking about validation of the data now. The purchasing service and the customer service, so you have to enter an order, so you have to validate the user.
Right. Yeah, that's a really good question. So the question is, how do I deal with data validation? Yeah, that's interesting. So I think it's dependent on the particular service. One, the authority of the user service. It has to maintain essentially a contract. Basically says, this is the information I have about the user. If you need user information, you ask me for it. Each service is responsible for validating data, the requests that come in, so they can, throw 400, is that what it was? Sorry, I lost my train of thought. Can you ask the question again? Or is that right?
Customer an order.
So if I have an incoming order object, how do I validate it?
Yeah.
So each service, so the order service that's receiving the order data it needs to maintain as part of that API saying, hey, this is the data I will accept, I will validate this message as valid. Anything else I will reject. And it's up to the people that want to talk to that to maintain that they're sending proper data. If an error occurs, I can emit an event into my centralized service and maintain a log of all these exceptions and things like that. But yeah, it's up to the individual services to validate the data, to maintain a specification that here's what I send out, here's what I accept. This goes back to the whole Conway's law thing, to make sure that these people, everybody's talking and that they understand what each service does and the data it sends out and receives. Does that make sense? Okay, Jeff, do you have a question?
The last one.
Last one, okay. Yeah, they talk about this afterwards.
Yeah, we'll talk afterwards. It's probably easier.
Okay. I think that means I still have time for more questions, but all right, no. Thank you, everybody.